Welcome back, students. In this video we are going to learn about type of loading and how do we analyze the uh, bridge and how do we calculate the bending moments and shear forces. Now we are going to detail the reinforcement of a slab or a deck slab bridge we are going to see in this video. So in the previous class we have learned about the introduction part, what are the type of the bridges and what are the factors of in which you wanted to select a bridge. So as per the syllabus is concerned, we do have only two types of bridge. One is the slab type bridge, and then we have a T-beam and a T-beam with cross girders. The reinforcement of the concrete slab is very important because much of the loading and the dynamic load is taken by the slab itself. So we have learned in the previous video that normally the slab type of bridge is taken when the spans are less than 8 meters, and when the span is more than 8 meters, or at least to 10 to 25 meters, then we go for a T-beam, where you have a series of longitudinal beams and a series of cross girders. Then over it we have a slab. So in this video we are going to design like slab bridge after the continuation of the discussion about loading. So normally the analysis is done based upon the loadings. So IRC 31/2000 has given you the classification of loading where you can consider. Normally we have four types of loads. One is class AA, class A, class 70R, class B, class A. So these four types we take the worst effect, and then we finalize the bending moments, and then we calculate them. So suppose this is the cross girders, and this is the main girder we are having, and when a single concentrated load, it is when you apply a single concentrated load on a slab. Let us say this has a slab and this has a B having a length B, and this has L. So when you apply a point load of P kilonewton on a slab, and it will the load will disperse a 45 degrees angle along the slab thickness. So the effective width at the bottom we have to take into consideration when you are calculating the net loading. So this concentrated load of P kilonewton should be converted into a area load of units kilonewton per square meter. So whatever the area which you are dividing the concentrated load is calculated based on the effective width calculation, and here there in code ISO 31 is clearly given how to calculate the effective width of the slab. So when we are doing a problem, we will go through it. So this is the 70. We do have the loadings. This is class AA. The class AA gives the worst effect of loading. So class A consists of a tracked vehicle of total length of 70 to 100 mm and a wheel width of 3600. On which direction we have the out to out dimension 2900, and each tracking wheel will give you a loading of 35 tons. So total we can expect a 700 kilonewton from a tracked vehicle. So as a tracked vehicle is also there, we do have also wheel loading. A wheel loading, we do have a series of train loads, and each loading of different. So the inner wheel loading we have 6.25 tons, and outer wheel loading we have 3.75 tons. So we analyze the bridge section with suitable proportions with these two loadings. Then we calculate the maximum bending moments and shear forces. Then we detail in cross section. So let us go into the problem. So let us take an example of designing a slab culvert for a state highway for a carriageway of two lanes, each of 7.5 meters width, and M20 grade concrete and Fe4 steel, having a clay span of 6 meters, which is less than 8 meters. So we can go for deck slab. Then we have a varying coat then bearing width. So here in the question it is clearly mentioned class A or AA, as because AA gives the worst effect, we'll have to consider AA loading. So we assume the depth of the slab as 80 mm per meter, so it comes about 500 mm. Then we calculate the dead load of the slab and the bearing code. Then from tracked AA tracking vehicle, we have impact factors from IS 31, sorry. Then we calculate the effective length of road. Then as discussed earlier, we calculate the effective width of the slab. Then the entire loading is divided with the area. So the loading average intensity of loading is calculated. From this average intensity of the loading per meter length along the slab is calculated. From that you can get the live load bending moment, and we do also have a dead load bending moment. We calculate both of them separately, then we add them up. So from this bending moment we'll calculate the amount of steel which is required from working stress principles. So the whatever the steel we have got, we calculate the spacing, suitable spacing for it, and we do also need to follow the design principle or design considerations, the minimum and maximum spacings, and we detail the following. The figure shows you the detailing of this slab. Thank you. We'll discuss about bunkers and silos in the next video. Thank you.